I do want to thank, this is joint work with numerous people. Mom, I want to thank first of all. I think where I've arrived is certainly the product of the help of a lot of people, and I definitely want to recognize them. I also want to recognize my father, and also my aunt, who was a really important part of my life as well, and also the love of my life, my wife, who I met in Barcelona, and of course my son, who's off in Australia right now. So just a little bit about, I'll say some things about me, but first I want to give some background on my family. My mother and father left Colombia separately. They hadn't met before, from Manhattan around 1964, and they wanted to be there. And they moved to LA in 1966. They broke up in 69 or so. They actually were never married. However, both stayed in Santa Monica. So there's a bit of privilege there, and I find it interesting. I guess maybe at that time, or maybe decades earlier or so, divorce was a big deal, and maybe it was frowned upon, and perhaps not being married is frowned upon even more. But here I am. So this doesn't seem to be a problem nowadays, and so that's a little bit of privilege. And also, they happen to both stay together, which is which I truly appreciate. And maybe another remark is that, of course, having parents that are split up, it makes things difficult. Maybe some of you have been through this, and being good Latin parents, I guess, they maybe they tend to bicker sometimes. And it's interesting. I learned editing very, very early because I would have to pass up messages from one to the other and back again. So I guess maybe I had to develop some talent for editing, maybe because of that reason. I don't know why. But another remark too is that having to spend time in two houses, I guess I was very accustomed to being in two worlds or trying to appreciate two things at once. And so I find that often I try to do two things at once. I didn't want to study algebra or geometry. I wanted to study algebraic geometry. And I didn't want to study just algebraic geometry. I wanted to study algebraic geometry and complexity theory and so forth. And I have other interests as well. So my mom worked as a nurse and cleaning houses, and my father worked as a welder in local union UI 250. And Sueli, she's from Brazil, and we met in Barcelona some years ago. And that was thanks to a conference co-organized by my advisor, my thesis advisor. So there's definitely thanks that I owe there to him, meeting the love of my life. My wife earned her PhD in Hispanic Studies from Texas A&M, rather late, maybe as a result of all of her travels. Her thesis was really awesome. It's a 406-page exploration of the image and representation of Gitanos, the Roma people in Spain during 1950 to 1970. So it's an entirely different world from mine. I would actually argue that her story is way more interesting than mine. So if you want to hear it, just let me know. My son Victor was born in Hong Kong. He traveled there for an academic position. And now he's earning a master's in visual effects in Australia. So to say maybe a couple more things about my academic background, I do want to mention Gretchen Davis. She was a high school teacher who I'll mention in a minute, got me back into math. And Basil Gordon, who was a professor here at UCLA, passed away a few years ago. And Steve Smale, my advisor. So after losing interest in math, I definitely lost interest in math around 9th grade. I had a teacher who basically was putting in no effort, and I really lost interest, literally. And Miss Davis really made it fun again, and so I really owe a lot to her. I mean, she was a fantastic teacher, truly, truly a remarkable teacher. And Professor Gordon was also a tremendously generous mathematician. I, at that point, was very, very enthusiastic about mathematics, and so I was majoring in engineering, and I was literally flunking out of my classes and doing math instead. And so I just audited math classes. I'd hang out in Professor Gordon's office. I was interested in the Putnam exam, and so I'd talk to him about problems. And I would literally spend hours a day, literally. And looking back, I'm wondering why he didn't kick me out. I mean, he was extremely patient. I'm not kidding. I spent 5 days a week in his office, so for some years. And I learned most of my mathematics with him. And by accident, later on in Berkeley, I met Steve Smale, actually at a particularly dark moment, and I asked him to be my advisor, and he agreed. Don't know why. Anyways, I did want to mention a story about red tape and blue liquid paper, and the story is as follows. When I was 15, because of Mrs. Davis, I was really enthusiastic about math and I wanted to take calculus over the summer as a 15-year-old. And so I did all the legwork. I went to different offices and tried to get approvals. And I finally got permission to take calculus in fall instead of the summer. So I took some liquid paper over the forum and I changed it into summer. And then that's how I took calculus over the summer. So I'm kind of a pseudo administrator now, so I promise you I follow the rules now. But but anyways, so I really want to emphasize. I mean, my advisors were truly wonderful. My mentors were truly wonderful. And I was very fortunate. And but on top of everything else, they were really fair and generous. And so you know, I didn't look like them, they didn't look like me, but you know, they treated me like anybody else. I was very fortunate. Graduating wasn't easy. There's some complications along the way. As an undergrad, like I said, I studied engineering, then I was flunking out of my classes and going to math classes instead. So I had to switch majors in order not to flunk out. And so I took a pile of math courses officially, like in my last 2 quarters here. And officially, I guess I could have graduated, except there's this one requirement having to do with residency or something. So that was going to be an issue, but thanks to a dean, I managed to get that waived. And in Berkeley, I had trouble passing my qual exam. So the qual in Berkeley is an oral exam you have to plan. And growing up, I didn't have any academic advice. I mean, neither of my parents were sort of academics. My father didn't finish high school. My mother went to some nursing school, but I really didn't get intimate advice about academia from my parents. So I was literally in danger of getting kicked out from the PhD in pure math program. But a very kind secretary said, why don't you just switch majors? So I switched to applied math, and I got my PhD. So very simple solution. So, you know, officially I'm an applied mathematician, but I don't know what that means. So if there's any lesson out of this, it's never be afraid to ask for help. It's really important. And also don't be afraid to ask for opportunities. So there's lots of times where you think like, you know, maybe I should ask for something, maybe I shouldn't, but you know, go ahead and ask, really. Ask for help, talk to people, don't be afraid to. Okay, so I do want to say also that I learned a lot from my students. And so I've taught RUs for some years, and this is just a sample of a few of the students that I've taught. It's really been fun. And I hope that this program can continue. I know times are difficult right now, and there's a lot of uncertainty, and it's truly a wonderful program. I should also mention, I never went to an RU when I was an undergrad. And when I went to grad school, I had a lot of trouble. I mean, you are very lucky to be here if you're a student, because you're already connecting with a really wonderful community. And when I was an undergrad, I really didn't have much research experience. I had a lot of problem-solving experience, but I didn't have any particular vision about how to get a PhD, what to do research in. So I literally had no idea going into grad school what I was going to do. So in grad school, I really had ups and downs, and I was sort of bashing my head against the wall, and after some years I figured out, okay, I kind of like algorithms, I kind of like complexity, I kind of like things having to do with polynomial equations. But that took me 4 years. And I see a lot of you here. I'm very impressed. It's wonderful to hear so many really brilliant students. I hear students, you know, saying all kinds of wonderful things, and they already know where they're going. I literally had no idea. And so, and it's funny that I'm leading RUs now. So anyways, getting to the math. Real algebraic geometry, the study of real solutions of polynomial equations. But here's the thing, what does it mean to solve a system of equations? So there's some very basic questions that are more subtle over the reals than over the complex numbers. And so a lot of algebraic geometers, a lot of people typically work over the complex numbers for technical reasons, where the real numbers are actually more interesting and more important in a lot of applications. So the basic questions you could ask are, okay, are there any real roots to your solution, to your equations? And if there are, how many real roots are there? And if there's infinitely many, maybe the zero set has some special structure to it. Can you talk about how many pieces it has, how many kinetic components? That's an important question. And then getting even deeper, if you have some understanding of how many pieces there are to the zero set, what about its shape? And so if you want to get fancy, can you compute the homology groups for these pieces or the isotopy type in some explicit way? There's many of these questions you can ask. And I want to emphasize these questions are subtle, more subtle over the reals, because over the complex numbers, things just happen with probability 1. Over the reals, things happen in a stranger way. So even detecting solutions, most algebraic geometers know when you're looking for complex solutions, usually either there always are, or with probability 1, or there never any. There's sort of no in between. Whereas for the reals, you can actually have 10 solutions of probability 20%, and a million solutions of probability 1%. All these things can happen. And of course, there's even more basic questions. Once you have the solutions, how do you approximate them? There's always different, really, really important questions. So when I was thinking about giving this talk, I thought I was going to talk about systems of equations. I apologize. I'm just going to talk about one polynomial, many variables, okay? Because that's already subtle enough. And you'll see in a minute why it's subtle enough. All right, so the main result I want to give is a speedup for detecting roots. And I mean an algorithmic speedup. But more than that, actually, it's not just detecting roots, it's actually determining isotopy type. And I'll define what isotopy is in a minute. And this is for positive zero sets of certain kinds of sparse polynomials. So that's kind of my thing. I love polynomials, looking at them in terms of their monomial term structure. And that's something a lot of algebraic geometers don't do. But it gets to be very interesting, and it gets you into combinatorics pretty quickly. So this is joint work with Alperen Ergur, one of my former students. Alperen Ergur is the older guy. Weixun Deng is one of my current PhD students, and Grigoris Paouris is a really awesome mathematician in my department. And yeah, he's truly a great guy. Works in analysis and probability. Okay, so who of us would not be glad to lift the veil behind which the future lies hidden? Hilbert said that at the International Congress of Mathematicians in Paris in 1900. And I mention this because I want to mention some Hilbert problems. So there are two big problems. Hilbert mentioned these problems specifically. It was a list of 23 problems. He specifically mentioned 10 in this talk in 1900 in Paris. And among the ones that he mentioned are this one. There's something called Hilbert's seventh problem. And it's already kind of pretty subtle. So if you have algebraic numbers, alpha and beta, and you know that alpha is not 0 or 1, and if you know that b is irrational, is a to the b always transcendental? So that's a very cut and dry question. And just a reminder, just as an example, is square root of 2 to the square root of 2 transcendental? Okay. And just a reminder, transcendental, what does that mean? First of all, numbers algebraic if you can find a polynomial that it satisfies as a root. Okay, that's just the basic definition. Polynomial with integer coefficients, non-constant. And your number is transcendental otherwise. Okay, and it turns out, if you have had a course in topology, transcendental numbers are really, really frequent, but proving that something is transcendental is actually pretty hard sometimes. And it's sort of an instance of the hay in the haystack problem. Sometimes, sure, there's plenty of hay in the haystack, but where's the hay? Okay, so how do you prove that something is hay? So this is one of these kinds of problems. The other problem I want to mention is Hilbert's 16th problem. So believe it or not, these are related in some way. And it's a complicated problem, but I'll just mention the first part. The first part is, what are the possible dispositions of the ovals of a smooth degree D curve in the projective plane? So don't worry if this seems a bit weird. Just think of an algebraic curve, just a curve, it's the zero set, the real zero set of a polynomial in two variables with real coefficients. Projective plane, well, I have some nice, well-defined way of defining how things go to infinity. That's all it means. So as a really sort of basic example, if you look at a degree 6 curve, there are classical theorems saying you're going to have at most 11 pieces to the zero set. And there's also other theorems saying that the zero set will consist of ovals, okay, meaning something kind of like a circle up to deformation, or perhaps maybe a very long line, which goes off to infinity, comes back again.
Right there.
Okay. So, for example, if you want to talk about disposition, you have 11 ovals. Okay, can the 11 ovals just occur right next to each other like that? Or, I don't know, maybe just jiggle around a little bit. Is that possible? Or could they be inside of each other? What's going to happen? And so it turns out you can prove that does not happen. I'm not going to get into the details, but on the other hand, that can happen. So you can have your 11 ovals distributed in this way. One oval on one side, you have another oval, which is actually sort of a very long line that goes off to infinity, and the other 9 are over there on the other side. That happens. And you can also have some nestings of ovals. So some things can happen, some things can't. Okay? And so
just to be clear, that's the same as having just two nested orbitals, right?
Let's see. Not quite the same. I mean, well, and for this one at infinity, the one that goes off to infinity, yeah, on one side, it's nested. But on the other side, you have 9 of them.
Right.
Okay, so, yeah. So that's the part about infinity that's funny. You can sort of move it around. Yeah, you can change it into a nested of 2 and then 9 on the outside. You can do that. Thank you for asking. Okay, so what possibilities? Can you classify these things? And it's a very, very hard problem, and actually it's still open. So okay, isotopy, what do I mean by that? Okay, I'll give you the technical definition. I'm not going to go through it, but the upshot is that an isotopy is simply, or rather an ambient isotopy in Rn. It just means a deformation of space, a continuous deformation of space, and your subset of space is sort of carried along for the ride and turned into another shape. So, for example, a coffee cup is isotopic to a donut, although putting in the sugar and the color is a little bit different. But anyways, the conditions are that you actually have a family of continuous maps, homeomorphisms that do this for you. So there it is technically. You can stare at that if you like or not, but that's intuitively, that's what's going on. And what's interesting about isotopy is that certain things that appear to be the same rather are not ambiently isotopy. So for example, a circle and a trefoil knot, of course, they're both topologically circles, but they've been embedded in different ways. And so you cannot actually deform R3 in such a way to change the circle into a trefoil knot. You cannot do that. Okay, you can prove that. And that's what algebraic topology does for you. Okay, so that's just a little bit of background. So getting back to Hilbert's 16th problem, well, there's a connection. And it has to do with something which happened in 1970. So in Nice, France, in ICM again, Alan Baker gets the Fields Medal for his theorem on linear forms and logarithms. So I'll say something more about that theorem in a bit. But the point is that theorem was a fantastic tool which gave a solution to Hilbert's 7th problem, a positive solution, as a mere corollary. So it turns out that if you look at Baker's theorem from the point of view of real algebraic geometry, you actually get some kind of an interesting unification of those two problems, which I'll get into. All right, so getting back to Hilbert's 16th problem, this thing about real solutions, there is a complete classification for all the dispositions for degree less than or equal to 7, and that took a lot of work, a lot of mathematicians, and forgive me if I don't list them all there, pre-2013. It turns out you can take this to higher dimensions, and so this is kind of interesting. Arefkov and Karlamov, they showed that if you look at the same problem for hypersurfaces, then the number of possible isotopy types is massive. Okay, so the point is that if you're going to get a classification, it's going to be really complicated with a lot of possibilities. Okay, so I'm not even going to go there, but I'm just telling you that you'll get doubly exponential many types, even if you fix the degree, if you increase the dimension. So I'm going to change the problem around. How hard is it to identify the isotopy type explicitly in the fewnomial setting? So what I'm going to do, instead of thinking of polynomials in terms of the degree, I'm going to think about them in terms of the number of monomial terms. And something interesting will happen. These will get a lot easier, even though the degree is incredibly high, and even though the dimension might get really high. So here's my notation. I'm going to have one polynomial, many variables. A Laurent polynomial will allow negative exponents. I'm going to write it out in that particular form. So CI's are the coefficients, the AI's are the exponent vectors. So in particular, I'm going to restrict the coefficients to be integers, plus minus 1 up to plus minus h. A is going to be the collection of exponent vectors. And to make things precise, I'm going to restrict the coordinates. So they're going to be between negative d and d. So it's something like the degree. Something like the degree. All right. So any polynomial can be written this way. But what I'm specifically focusing on is the n and the k. Okay, how many terms are there? So, okay, that's my exponent set. It's big A. And I'm going to have some kind of mild geometric condition. I'm going to assume that the rank of this matrix which I just built is n plus 1. So this is just to avoid some silliness. So if I don't make that assumption, then I can take examples having 17 terms in 51 dimensions and do a change of variables and get it down to lower and the smaller number of variables. So I just want to avoid that problem. So the notation, again, I'm using multi-index notation. So when I say x to the AI, x to a vector, I mean a monomial in n variables. That's what I mean. All right, so I'm going to call this an honest n-variate n plus k-nomial with support A. That's what I'm going to call it. And just to give you some examples of these different A's that I can get, when k equals 1, when I have n plus 1 points in n dimensions, well, in dimension 0, I have a point. Dimension 1, I have 2 points. That gives me a line segment. These are examples of simplices. So in 2 dimensions, I have 3 points, et cetera. So these are sort of, if you're looking at this from the point of view of combinatorics or geometry, these are the simplest points that you could ever find. Okay? And yes, you can think about polynomials whose exponent vectors look like these sets. And if you increase the k, it's more complicated. So that's the simplest case. And for k equals 2, you get slightly more complicated point sets. Okay, 4 points in 2 dimensions, rearranged that way or that way or that way, or any number of dimensions. It doesn't matter. So that's known as the circuit case. And it's an unfortunate terminology. Yes, there are circuits in complexity theory, which I could talk about, not in this talk. And there's also circuits from combinatorics. Okay? All right, so we define what my point of view on polynomials. Let me start getting into some additional things. I have to talk about input size, because I'm going to talk about algorithms. If I'm going to say how hard something is, I need some way to measure the size of the thing that I'm talking about and the time I'm going to take. So when I have a polynomial of that form, the size is defined to be this weird expression. Long story short, is just how much ink it takes to write down the monomial term expansion of the polynomial. That's all it is. Because you're adding up basically the number of digits and the coefficients and the number of digits and the exponents. That's all you're adding up, and up to the log. What base? Well, I use base e. So up to a constant is just the number of digits and how much ink you're wasting. So as an example, a polynomial of that shape, the coefficient is h, and that last exponent is d. Well, it winds up being something on the order of log dh. Okay, and I'm using this computer science O notation. So yeah, it's equal to something bounded above by a multiple of log dh, constant multiple of log dh. Okay, and it's important to distinguish this because in older literature, people use a different notion of size. So I just have to point that out. Logarithmic height, it's a really important quantity coming from number theory, but it's actually pretty easy. It's the same thing for fractions. How much ink do you need to spend to write the fraction down? So the logarithmic height of a fraction with relatively prime numerator denominator is just the biggest logarithm out of those two guys. And you also define the height of 0 to be 0 just as a default. All right, so that's a way to measure the size of polynomials. It's a way to measure the size of a rational number, the complexity of a rational number. And what do we want? We want algorithms to be fast. And so one way to be fast, a soft way to be fast, is to have it run in time polynomial in the input size. All right, so now we could spend a lot more time talking about computational models and stuff. So the computational model, just take it to be my laptop. Okay, so time is equal to number of bit operations. You can fix any machinery you want within reason, a Turing machine if you like. And there's classical theorems saying that up to changing exponents, it's really all the same. So we're talking about polynomial time versus exponential time. So when I want an algorithm to go in polynomial time, in my notation, it's going to be something of this shape, n plus k times log dh to the O of 1. Okay, so there's some constant. 10th power, 20th power, I don't care. I don't want to be exponential in that. Exponential is going to be slower. So I just want to point out the classical computational algebra usually takes time of that nature. There's bigger bounds. So if you take anything away from this talk, you should just recall that algebraic geometry computation is pretty hard. Pretty much everything you do in algebraic geometry is going to be NP hard. It's going to be taking exponential time or polynomial space. And we want to go faster. And the way we're going to go faster is by making use of sparsity. So it turns out you can do things with really, really high degree, with few terms, and suddenly things go faster over the reals. OK, so wait, there's a problem, though. We're already going to hit a wall. So it turns out that detecting real roots is already NP hard for just one sparse polynomial. So let me explain that. First of all, I should explain P and NP. That's going to take a while, but let me just say what I want to say. You fix any small epsilon. So let's suppose for the moment that there's an algorithm that'll take any polynomial with n variables, having at most n plus n to the epsilon many terms, so just a little bit more than n terms, and tell you if there's a real root or not. So if there is such an algorithm and it runs in polynomial time, then p is equal to np. Okay? So what this is telling you is that this is a hard problem, and it's going to be unlikely to find, it's going to be unlikely there exists a polynomial time solution. I mean, most people believe that p is not equal to np. And, well, if you find a polynomial time solution, then you'll get p equals np. And you will destroy cryptography, and a lot of people will want to hire you and give you awards. Maybe you can't lose either way. Okay. So you could try proving that problem is NP hard. I'm sorry, you could try proving the problem is legitimately exponentially hard. That's a different problem. All right, so that is an obstruction. But notice that I said n plus n to the epsilon. What if I just take n plus a tiny bit more, like n plus 1? So here's the thing. For n plus 1 nomials, it's a cute exercise for your students that there's an O of n time algorithm for deciding if the zero set is empty or not. It's actually not hard at all. And remember, I'm allowing arbitrary degrees. So you can talk about degree 4,000, degree 1,000,000. It doesn't matter. So as long as you have n plus 1 terms in n variables, and you're detecting real roots or positive roots, that's easy. So here's the theorem. In the simplex case, in this case of n plus 1 points in space, the zero set is empty if and only if all the coefficients have the same sign. So it's kind of a dumb result, but it's an important one to remember. So if you have a polynomial and all the coefficients have the same size, sorry, z plus, I just mean the positive zero set. I mean the zero set in the positive orthant. All the coordinates are positive. So one side of this is really dumb. If you have a polynomial in, I don't care how many variables, I don't care what degree, but if all the coefficients are positive, if you plug in a positive number, you're going to get something positive, you're not going to get 0. So if it's obvious there's not going to be any positive zeros. But the converse is true as well. So proving that is a nice exercise for your students.
Right.
So the simplest case also gives you the first glimpse of tropical geometry. Okay, so now I'm going to say a little bit about tropical geometry. Oops, can't find my clock. There. Okay, so I'm just starting really, really basic. So if you take, coordinate-wise logarithm of the absolute value of the complex roots of a binomial. Let's take a binomial, something with 2 terms and 2 variables. So you take the coordinate-wise logarithm of the absolute value of the complex roots. What are you going to get? Well, it turns out you get a line, and it's perpendicular to the Newton polygon of this polynomial. So let me explain all that. So here's the picture. So to any polynomial, I can naturally associate something called the Newton polygon, Newton polytope, and it's a very simple construction. Look at the polynomial, look at its terms, look at the exponent vectors. Well, the x1 to the 4th, that's the same thing as x1 to the 4 times x2 to the 0. The x1 cubed x2 eighth, well, that's the same thing as x1 cubed x2 eighth. These correspond to points. So look at the exponents, 4, 0, 3, 8. So I plot those 2 points, I take the convex hull. The convex hull of 2 points is a line segment. Okay, so I get a line segment. Well, funny coincidence, if I look at the complex roots, okay, now that's complicated. Like, I have something in 2 variables linking complex roots. That's weird. But never mind. Let me take the coordinates, take absolute value, and take log. What do I get? I get literally a straight line. And you could prove that in one line. Okay, so if you take that equation, set it equal to 0, well, you put one term on the other side, you get monomial equals monomial, take log, and you get a linear equation in logs. Okay, it's really easy. So you literally get that. Coincidence, maybe not, it's perpendicular to that Newton polygon, to that edge. That's kind of interesting. So that tells you some information about the complex roots, and this is actually very classical and very old. Engineers have been plotting solutions on log paper for decades. And this is an example of working with log paper. Oleg Viro, a great geometer, mentioned this. And he said, yeah, if you plot polynomial zero sets in log paper, you get interesting, somehow things become a little bit clearer. Okay. So what if you want to do this with positive roots or real roots? So what happens if you do that instead? Well, if I try to do the same trickery, I get nothing. But that's fine. I shouldn't get anything because that's a polynomial with positive coefficients, so there's no positive roots. So I shouldn't get anything. Okay. And indeed, if I change the sign, then I get 2 different signs on those vertices, and then I do get a line. So what I'm getting at is that when you look at binomials, the binomials where all the coefficients have the same signs, well, they give you nothing. But the ones with alternating sign, give you an alternating edge, they give you something. This generalizes, believe it or not. So that's the beginning of tropical geometry. So if anybody tells you, if you ever think that tropical geometry is complicated, it's not that complicated. It's really just about things canceling. That's all it's about. So now let me define a tropical variety. So this looks a bit weird. Okay, this is a bit complicated. To define a tropical variety, you're going to play the same trick, but now you're going to do this in regions. Okay, there's going to be regions where certain monomials dominate and certain monomials are smaller. And what you want to look for are regions in space where certain monomials dominate in pairs and everybody else is smaller. Okay, so that's exactly what the definition is saying. And I'm also putting in a condition about the coefficients having opposite sign. Okay, so that's a modification of the notion of tropical variety. Tropical varieties started off in a different world, and they're typically used in a fancier setting. They're used in the setting of non-Archimedean fields. And I'm just doing this, from scratch over the reals. So as an example, let's take something more complicated. Yep.
C prime you're saying is doubly clear.
Let's see. No, sorry. I'm just talking about two coefficients. So.
What is doubly?
Yeah, I'm sorry. Y. It should be a dot y. I'm sorry, a dot w. Yeah, that's what I meant. Yeah, that's a typo. Yeah, I shouldn't have a y. There should be a w. Okay. So that's where the w is. So by putting in an exponential, I'm essentially taking logs. So, okay, one polynomial, two variables, three terms. What do I get with this? Well, if you look at the Newton polygon winds up being that. And how do I plot that? Well, again, it's the monomial terms. The first term is x1 to the 0, x2 to the 4, so I get 0, 4. Next term is x1 to the 4, x2 to the 0, I get that. Next term is x1, 3, x to the 8th, I get that. So that's my convex hull. Convex hull, 3 points of the triangle. And I claim that if you think about this alternating edge thing, like, looking at the signs, you'll get something interesting. So if you think about the signs, those two signs are positive, corresponding to those points, those monomial terms. That one's negative. I claim that you're going to have somehow a line emanating from this edge and a line emanating from that edge. That's just going to happen. Okay, that's what I claim. And that other edge is going to give you nothing. And that turns out to happen. So it turns out that what you get is an elbow. Okay, so you get a ray going one way, you get a ray going the other way. These rays are going exactly perpendicular to those edges. And the true positive zero set, when you take log of it, is that red thing over there. So you see, wow, okay, that's interesting. Not exactly plotting the same thing, but you notice that as you go out to infinity, they get closer. And that's the nature of tropical geometry. Tropical geometry, at least in the Archimedean setting, is giving you a lot of information about things going to infinity. And what happens inside is different. Now, I can actually tell you an upper bound of the distance between these two guys. Tropical varieties actually, in this setting, approximate with some metric guarantee. Coarse approximation, but I can bound it. So this goes way back. I mean, it goes back to work of Hadamard in the 19th century, Ostrovsky, early 20th century. I wrote a paper about this. So we have explicit distance bounds on this. Okay, so that's your introduction to tropical geometry in 5 minutes. Okay, so I'm going to push this farther. So this works in all dimensions, I just want to emphasize. So here's a little example. So this is something, one polynomial, two variables, 4 terms, and it gives you something in 3D. What you're seeing, that green shape, or at least the stronger green shape, is a positive tropical variety, kind of truncated. You see this ghost of other things. That ghost of other things is something having to do with the complex roots. But you see this thing, actually, it looks kind of like a potato chip or something. And really, up to isotopy is just a hyperplane. Okay, so basically, you can take this whole thing and sort of flatten it out and make it a hyperplane. Okay, so it's part of a more general theorem. Okay, so this works in higher dimensions. All right, so let me get back to here. Okay, so affine relations. So I'm going to talk mainly about circuits at this point. So I'm going to go even more complicated. I'm going to do n+2 terms and variables. So a circuit combinatorially is just a point set, n+2 points in z to the n. I form this matrix A hat, and the condition is that the rank is n+1. And for such a matrix, the right null space, the kernel of that matrix as a linear operator, is going to be generated by one vector. Okay, so I'm going to let B be a generator, and I can also let B have integer coordinates with GCD equal to 1. I can make that assumption. Mm-hmm. So what's going to happen is that the sign of B, the signs of the entries of B, is going to be important. It's going to tell us a lot of combinatorics, and it's going to give us information about the zero set in the end. So here's what I'm going to define. There's something called the radon partition. So when you look at this generator, geometrically what's happening is that that generator is going to tell you about the affine relations. What kind of linear combinations of points under certain restrictions will give you 0. So here's the example. So for 3 points in the line, that's a circuit. The B vector, doesn't matter what the coordinates are, will be positive minus positive, okay, or minus plus minus. For something of this shape, the B vector will have 3 pluses corresponding to those points on the outside, and the red point is going to have the opposite sign on the inside. And that's another example. That guy over there is a little bit different. So that's called the degenerate circuit. I just put in there for completeness. So all right, the B vector, I'm not bothering to compute it, but the signs will be one of these choices, plus, minus, plus, or minus, plus, or minus. Okay. So a little bit of linear algebra. So what am I getting at? Well, it turns out that you want to look at zero sets. And if you want to look at zero sets, there's an important case. There's something called the incompatible case. So if you look at the coefficients and the b vector, and you look at how the signs change, then if you don't have the sign being constant for all I, the positive zero set is either empty or isotopic to a hyperplane. Okay? So basically what I'm doing here, or what my student Deng did, he sort of knocked out a lot of cases. Unless the coefficient signs and the b vector signs align in the right way, then you're going to be in a really super easy case. Okay, that's what the lemma is saying. Okay. So as an example, if you look at a polynomial with one variable, three terms, like that one or that one, neither one of them is compatible with this with the circuit. And as a result, they either have no roots or just one root. Okay, that's a really easy thing to knock out and not hard to compute. So now let's assume we're in the compatible case. So the signs of the coefficients match up, and the signs of the b vector match up, and go from there. So I just want to point out the probability of being compatible is rather small. So the compatible case is harder, and it also ends up being rare, because for signs to line up in exactly the right way, the probability is basically exponentially small. Okay. So but we're being complete. We're handling everything. So the next step is looking at discriminants. So sorry, one thing I want to point out. We're ramping things up. So we started with a polynomial in n variables, n plus 1 terms. Things were easy. Now we have a polynomial in n variables, n plus 2 terms. Things are getting harder. And what's going to happen is that the coefficient values themselves, not just the signs, are going to matter. So when you're looking at n plus 1 terms, all you care about is whether all the signs are the same or not. It's stupidly easy. When you look at n plus 2 terms, then it actually matters the proportions of the coefficients. All right, so you have to look at discriminants. And so the discriminant is this interesting quantity here. So it goes back very far, but one place where the discriminant was really definitively treated is the work of Gelfand, Kapranov, and Solovinsky in the 90s. So here's a weird-looking function, which I claim controls everything. So it's some function involving the b vector and the coefficients of a polynomial. All this can be computed relatively easily. And let me give you a concrete example. If you look at this polynomial, 4 terms, 2 variables, the last term has a parametric coefficient. The coefficient is c. Okay, I'm going to vary c. So if c is negative 23, the true zero set is the red thing there. It's like an oval. If you look at c equals minus 6, the true zero set is just a point, that little dot there. If c is in this range, negative 6 to plus infinity, then the zero set is empty. Okay? So we'd like to be able to detect this. How do you detect algorithmically? Is the zero set an oval? Is it a point? Or is it nothing? How do I detect this? Well, it's exactly the sign of the discriminant. Okay? So if you compute the sign of the discriminant, negative gives you that oval, 0 gives you a dot, and positive gives you empty. Okay, so it exactly detects everything. So okay, great. So we managed to find some kind of criterion, but now the problem is, how do I compute this discriminant? Because if you think about it, this discriminant is a bit weird, because you potentially have really big b's, and then when you have big coefficients, you have large numbers, large integers to large integer powers, and that can be massive. So we have to think about that. So I'll get to that. Let me talk about the classification. So this is joint work with Frederick Behan, Erica Croy, Weixun Deng, and Caitlin Phillipson, and Joseph Rennie. And the main theorem is the following. If you look at the sign of the discriminant, let it be epsilon, so negative 0, 1, and you let a plus a minus be the Ranoff partition for this point set, then the positive zero set is isotopic to the real zero set of a quadratic polynomial, explicit quadratic polynomial. Not only that, the polynomial has plus minus 1 coefficients. Okay, so I give you something absolutely explicit. So I don't care what polynomial you give me, as long as it has n plus 2 terms, n variables, could have any exponents. All you have to do is compute the b vector, compute the sign of the discriminant, and I can give you a very, very simple quadric with the zero set that finds everything topologically. So in particular, such positive zero sets always have at most 2 pieces. So look, I can talk about polynomials of degree 1,000,000. The fact that they have n plus 2 terms chops the zero set down to 2 pieces. Okay, that's kind of a nice corollary. And also, the positive zero set can have two pieces if and only if something particular combinatorial happens. All right, now let me highlight this, the sign of this discriminant and this epsilon. So I'll give you a concrete example. If you look at this polynomial here, so this is 3 variables, 5 terms. First coefficient and last coefficient are going to be moving around. So depending on delta being positive, 0, or negative, something's going to happen. So let me give you a little movie. So what's going to happen is that depending on the sign, if your sign is positive, then your tropical variety looks like this, and it actually winds up being something isotopic to a particular shape. So what's this isotopic to? Anybody want to say?
It's
A cylinder, yeah, it's actually a cylinder. And a cylinder is, as you know, the zero set of a quadratic polynomial, okay? So there's that example. If the discriminant is 0, then you get the degenerate case, and the degenerate case, there you go, winds up being something isotopic to a double cone, okay? So quadratic singularity. Okay, so it's polyhedral, but up to isotopy is just a double cone. And if the discriminant winds up being negative, then you get this thing here. Perhaps you can tell me what it's isotopic to. Yeah, it's a two-sheeted hyperboloid, or if you like, 2 hyperplanes. And so the thing is, okay, it looks complicated, but I've given you an explicit quadratic. More to the point, this is classical. This goes back many centuries. When you're looking at the zero set of a quadratic, it's easily writable explicitly as a product of a sphere of a certain dimension times a hyperplane of a certain dimension. That's all it is. All right. So getting back to this classification, where's the algorithm? Slideshow. There we go. All right. Where's Baker's theorem? So I can finally say where Baker's theorem appears. You see, deciding the sign of that discriminant, well, remember that discriminant was some kind of weird product of powers minus 1. And now I have to decide if that's positive, negative, or 0. Well, put the 1 on the other side, take logs, I get a linear combination of logs. In fact, it's integer linear combinations of logarithms of rational numbers. All right? Well, that's exactly what Baker talked about in 1966. So he has this beautiful theorem. If you have alpha i's being positive rational numbers, bi's being integers, and if the log of, this fancy a is the maximal, log of a is defined to be the maximum height of all these alpha i's. Capital B is the maximum of the logs of the bi's. Okay? Under those conditions, if I let lambda be that linear combination of logarithms, here's what's going to happen. Linear combinations of logarithms are either going to be non-zero or 0. We want to know if they're positive or negative or 0. Baker's theorem tells you that there's a discreteness to this, meaning that if this thing is non-zero, it's going to be pushed away from 0 by an explicit amount, or it's going to be 0, nothing in between. Other classes of functions, you can get arbitrarily close to 0, but linear combinations of logarithms, there is a certain kind of quantization. You stay away from 0. So here's the bound. If you're not 0, then log of delta, remember, if delta is really tiny, then log of delta is going to be really negative, but you can't be too negative. That's the bound. Negative O of log A to the m times log E. So that seems pretty big, but actually that's good enough for applications. So we have to recall something else. This is telling you how much accuracy you need if you're going to approximate those logarithms. That's how we're going to do this. We're going to compute the sign explicitly, correctly, by approximating the logarithms and using Baker's theorem. That's what we're going to do. So there's a classical theorem. I mean, I'm using Bernstein's version. This is Daniel J. Bernstein, brilliant cartographer in Chicago in Germany. There's a complexity bound. So if you want the L most significant bits of log, it takes you time close to linear in L. So put those two things together. And also Bernstein's results, he has a very nice write-up of this, but it goes way back. It goes back to Brandt and Salomon and other people. And I think Gauss knew the iteration. So corollary, you can find the isotopy type of the positive 0 set of any circuit polynomial in time that. Okay, so that is, unfortunately, not polynomial time. It's exponential time. But it's way better than anything you can do with computational algebra. So I'll just say quickly that the classical techniques that people would use, critical points, Gardner bases, and all this other stuff, would just kill a computer. Okay, so try it. I mean, you try 10 variables, try 20 variables, you're going to get an out-of-memory error. You get nothing. But this algorithm actually is pretty practical, except that you're using an excessive amount of accuracy. It turns out that Baker's theorem is very pessimistic, and maybe the reality is better. So let me point that out. So first of all, the complexity bound looks big. Yes, it's exponential, but it's way better than what was known before. Well, here's the thing. There's a conjecture in 1978, the Lang-Waldschmidt conjecture, which is much, much more optimistic. Now, it's just a conjecture, no proof of it, still. And proving this would be wonderful. And I truly wish I was a better arithmetic geometer. In fact, you can also prove it via the ABC-Conjecture. In fact, if you had a strong version of the ABC-Conjecture. I'm not going to get into that right now. But here's the thing. This is not the most practical way to do it. So yeah, I'd love to be a more powerful arithmetic geometer, get a couple of awards and prove that, but it's going to be kind of hard. So there's something more practical you can do. So the more practical thing you can do is what I did here. You take those parameters as before, and you let your b live inside of there, and you let epsilon be within a certain range. And now you're going to randomize. So what we're going to do is get a randomized version of Baker's theorem. We're going to prove that Baker's theorem actually admits much better, much more realistic accuracy most of the time. That's what we're going to do. And this is really odd because I checked with my number theory friends and they were unaware of any such result. So now we have one. So here we go. Under these assumptions, uniformly random alphas, then you have this, which is incredibly better. It's way, way better. I wish I could say that this is entirely us, but what we did is we applied something from another field. So this is going to happen with probability 1 minus epsilon. Okay, high probability, we have a really, really good bound, much better than Baker's theorem. And this follows from a powerful result coming from anti-concentration theory. So probability is pretty powerful. And we just happen to apply it in this way. And there's another consequence. So I put a picture of a purple swan there. So this is, all of this work is trying to get rid of these purple swan events. So the complexity in this setting is occurring in some really rare events, but we have to handle them. And now we're going to get rid of them with high probability. So the corollary is that if you look at any circuit and under certain parameters, then for a very large fraction of the inputs, the polynomials, you can compute the isotopy type in polynomial time. So that's the final result. So you can compute things in polynomial time with very, very high probability. And again, I emphasize that we're dealing with polynomials in many variables, very, very high degree, and not a problem. The reason that we can handle them is because it's n plus 2 terms. So the obvious next question is like, okay, what about n plus 3 and n plus 4 and so forth? That's in the works. The other question is polynomial systems. That's a whole other talk. But that's where I wanted to sort of end the math. And let's see. So anyways, I just wanted to thank you for your attention. And before we go further, I wanted to thank the organizers. I have trouble remembering names on the spot, so I'll just say thank you, organizers. You did something wonderful, so thank you very much.